Again, thank you for the introduction, and thank you everybody for your attention over the next 45 minutes / 1 hour, depending on how much I will be talking. My name is Lorenzo Gazzola. I'm the European Application and Business Development Representative of Zaiput Flow Technologies. And in today's presentation, we will be talking about liquid extraction technology for continuous and batch chemical processes. In my role at Zaiput, I support our European customers, both for all the, let's call them commercial inquiries. So if you need one of our devices, you will get in touch with me if you're based in the UK or somewhere else in Europe. But even more importantly, I support our European customers providing technical assistance. So if you already use our devices today and you have any issue or any question with the device, I will be your point of contact. Again, it's really an honor to be here and presenting at this webinar. I hope you will find it interesting, and I know there will be a session for questions if you have some later on. So in this presentation, I prepared, first of all, an introduction on Zaiput, basically an explanation, a brief explanation on who we are, where we come from. And then after this, we will go more into the technology, which I believe is what is interesting for you, with a few applications taken from flow chemistry and then from batch chemistry. So at Zaiput, we started as an MIT spin-out that really existed to commercialize inline continuous separation technology for flow chemistry. What does it mean? It means that in the laboratories of MIT, we developed, or our founder developed, the liquid-liquid separator that many of you, I believe, already have in their labs. And it's the tiny guy you can see down here. So the company really existed originally to commercialize this technology that was developed at MIT. In the years, the company became much more than that. It developed into a bigger company, both in terms of people, of course, and in terms of product supply. So the first direction in which we became bigger was in developing bigger separators. So here you see our two larger devices and their fourth larger phase separators. So both liquid-liquid or gas-liquid separator. With the same device, you can separate any biphasic mixture. And the biggest one now arrives up to 2,400 liters per hour, just with one single separator. So when you think about your processes, think about that the Zaiput technology can help you up to 2,400 liters per hour. Then we moved into not supplying anymore just the phase separation, but integrating our phase separators with technologies for continuous extraction. So in the second section here, you see our platform for countercurrent, liquid-liquid extraction. So whenever you need multiple stages of extraction and in countercurrent, we can help you with that. We will talk about this later in the presentation. And then we get to what I think is really the main topic of this presentation, which is our platform for batch extraction. What does it mean? Of course, we supply a continuous technology, but there are situations where even if your reaction is in batch, you can get a lot of advantages in doing the extraction in a continuous fashion. And I will tell you what those advantages are. The fourth and last of our, let's call them product lines, are our back pressure regulators, which are devices that complete our flow chemistry offering, and they are developed specifically for the needs of flow chemists. In this slide, you can see the history of Zaiput. Zaiput existed for about 10 years now. We just recently celebrated our 10th anniversary. You can see the devices that were released over the years by our company. All of these numbers, so SEP10, SEP200, 3000 and 40K, so 40,000, they are an expectation in milliliters per minute of the throughput of the device. So if you take, for example, the SEP3000, you can expect with that device to hit 3 liters per minute, or of course 180 liters per hour. I say it's an expectation because you will see later in the presentation that there may be some factors that will slow down how fast you can push your stream, or you can accelerate. For example, viscosity. As you may imagine, a very viscous liquid will not be able to be separated at those high flow rates. But if you have a very not viscous liquid and maybe with a high interfacial tension between the water and the organic phase, you can possibly increase the throughput through the device with a certain device. In 2018, we sent one of our SEP-10, so the laboratory scale device, to space, to the International Space Station, and astronauts really did experiments with our device. The reason why, there are actually two reasons why we did it. The first one is that it's just, it's good advertisement for Zaiput. So after that experience, many people started talking about Zaiput. Of course, people like to hear about space. The second reason, which is the more scientifically important one, is that our device is the only phase separator that doesn't rely on the differential in the density between the two phases. So what does it mean? It means that if you're up in space, you can separate, because we don't separate based on gravity, based on the density differential, which is what all the other technologies for phase separation would do. But we separate based on the affinity that one phase has or doesn't have for the membrane which is installed in our device. And we will see in a little bit more details what it means. So, of course, it was interesting to test it in space, but it's important because when down here on Earth, you have situations where your two phases have the exact same density or a very similar density, which results in a very slow or impossible separation by gravity. We can separate. So keep in mind, density is just something that doesn't have any role in our separation technology. So as I said before, we already touched on this, but Zaiput is an American company, so that's where our devices are engineered, that's where they are manufactured, and that's where they ship from. I am based in Prague, which is a lovely city, but as you may tell from my name and probably my accent as well, I'm from Italy. I'm from Milan, but I've been living a few years in the United States and for the last few years in Prague. And once again, I will be your point of contact if you need to talk with the Zaiput representative. We are a growing company. Our devices have been sold already in more than 50 countries worldwide. We've been growing on quite a steady trend. Recently, we increased the manufacturing and office space in our site, in our headquarters in Waltham, in Massachusetts, in the United States, of course. And then we keep a very strong link with academia. We offer academic discounts on our products. We really try to develop new and interesting applications using our separator in academia. And I would say almost weekly nowadays, there are new papers being published with the Zaiput technology, and there are many, many interesting applications where Zaiput allowed a continuous separation. But now, enough with talking about Zaiput as a company. Let's go into the Zaiput technology, which is what I believe is interesting for you. So this is a work that has been published about 10, 11 years ago, so it's quite old, but I think it's still very relevant. So what this work showed is that the most common post-reaction step in a typical pharmaceutical process, but I think this applies to the chemical industry in general, is either another reaction or an extraction. And while there is a lot of effort, a lot of time spent in optimizing reactions, rightfully so, it's of course the most important step of a process, we thought that there was a market gap and a technological gap in optimizing extractions, liquid-liquid extractions, and of course, liquid-liquid separation. So that is why Zaiput exists, and that's the kind of the area where Zaiput provides its expertise and where we can improve your processes. So this little video is worth more than 1,000 words. Sorry. It basically is an explanation on what the Zaiput core technology, which is the phase separator, does. So in this video, you will be able to see a biphasic stream that enters the device. You will see a red phase, which is the water, and then a clear phase, which is the toluene. So just a simple demonstrative system. And then you will see how the device will separate the phases in the two distinct components. So I'll try to play the video now. And you can see, you cannot see the back of the device, but please trust me, there is no electricity going to the device. So the device is a passive one. There isn't a pump inside, or there are no moving parts. It's a passive device. It's a plug and play device. And what you will need is just a pump to push the stream through the device, and then the device will separate. Now, just for reference, the device you see in the video is a SEP 200, which is basically, again, SEP 200 because it can reach the expected maximum throughput of 200 milliliters per minute. So how does it work? As I said before, it's a membrane-based technology. And so, of course, we have a membrane inside of our device. This little diagram explains really what happens inside the device. So the membrane is indicated by this white dotted line. You can see that the biphasic stream enters the device. And at this point, one of the two phases will have affinity for the membrane. Regardless of the density, again, I want to clarify this once again, it's just a matter of having, for the membrane to have affinity for one phase and vice versa. So as you can see here, the membrane installed is an hydrophobic one. We offer both hydrophilic and hydrophobic, and you can easily replace them inside of the device. How can I tell that it's an hydrophobic membrane? Because I can see how it's the organic, the phase that permeates the membrane. So step number one is that once the biphasic stream arrives here, one of the two phases will have affinity for the membrane. I have another little video. I like videos. I feel like they can explain better than I can do. But this video shows you how water behaves on an hydrophobic membrane and hydrophilic membrane. These are membranes taken from our laboratory scale device. You can see how water doesn't wet the hydrophobic membrane. It basically beads up. While it does wet, you can see how it really fills the pores of the hydrophilic membranes. And of course, if you use an organic solvent, you would see exactly the opposite behavior. So once again, this is step number one. Step number two, though, it's not just wetting the membrane, but it's pushing continuously and entirely the phase that has affinity for the membrane to the other side of the membrane, so the organic phase in this case. How do we do that? We do that by means of a differential pressure. So we want the pressure on the non-wetting side to be slightly higher than the pressure on the wetting side, and we want to create a transmembrane pressure. And we're talking about a very small pressure differential, just a fraction of a bar. But that pressure has to be high enough to push all of the organic through, but not too high to also push the aqueous phase through. So again, high enough, but not too high. You understand that there is quite a thin range of pressures that allow us to achieve this continuous separation. How do we control the pressure? Of course, through our pressure controller, which is built in the device, which is a passive unit. And this means that there is no electronic control. You just have to flow in. The pressure controller is really just a foil of plastic. It's a plastic diaphragm indicated by this white curved line, which is quite strongly pressed against this orange dome. So you see the dome here, you see the diaphragm being pressed against the dome, and the non-wetting stream basically has to stretch down the diaphragm, flow between the dome and the diaphragm, and then finally escape the device. So this stretching force that the non-wetting stream will apply on the diaphragm basically creates a slightly higher pressure on this channel, and that's the reason why, regardless of your inlet conditions, the device will always keep the transmembrane pressure within the optimal interval. And then everything you need to do is just choosing the best membrane. As I said, there are hydrophobic or hydrophilic membranes, and then the membranes also change in porosity. You just pick the right membrane, and then you just flow in with your pump, and you will observe a continuous separation as in the previous video. Now, this is really the core technology, the core Zaiput technology. I hope it was clear. If something wasn't clear, I'm very happy to take questions later at the end of the presentation. So, as you can see here, these are all our scales for the technology. We go from the SEP 10 to the SEP 40K. I told you already that the numbers indicate the expected maximum throughput in milliliters per minute. The reason why the arrow interrupts here is because from SEP 10 to SEP 3000, the separation happens exactly as I showed you before. So we will have a permeating phase and a retentate phase. On the SEP 40K, we will basically separate in a slightly different way, because we will have two membranes, one hydrophobic and one hydrophilic. So both phases will actually permeate the membrane. And what does it mean? It means that when we scale up a process, let's assume you're testing your system on a SEP 10 and you can separate successfully up to 15 milliliters per minute. As I told you, there isn't really a maximum flow rate. As long as you can separate well, you can keep doing. If you can separate up to 15 milliliters a minute, so 50% more than the nominal throughput, it means that you can separate up to 300 milliliters a minute on the SEP 200, up to 4.5 liters per minute on the SEP 3000, and typically you can scale up actually more than linearly when you get to the SEP 40K. I will have a slide later on the SEP 40K so that it will be clear how this slightly different separation technology works. Some of the advantages of our devices are that the devices can work continuously. You can use them to separate liquids with the same density as I was saying before. They are very effective gas-liquid separators if you need to, for example, remove bubbles of gas from a liquid stream. They are really a plug-and-play device. As you've seen, there is no electricity. The scale up is absolutely easy and linear, and typically becomes more than linear on the 40K. So it's really, really easy to scale up. The chemical compatibility is excellent. All of our devices, or almost all of our devices, are available in perfluorinated polymers. There are alternative materials for the wetted parts, which are stainless steel 316 or Hastelloy. Long story short, even if you have very corrosive agents, we will be able to process your stream with no issues. If you need to run separations under pressure, we can do that up to 20 bar. They're very easy to use. The maintenance is very low. Really, the only maintenance there is to do is to replace the diaphragm about once a year to make sure it always provides that back pressure on the membrane level. And then you will have to replace the membrane, but that is more of a consumable type of operation rather than maintenance. And then they have a very small internal volume. If you look at the SEP 10, you're looking at less than 0.5 milliliter of internal volume. So even to run an optimization study, if your materials are very expensive, you really don't need a lot of material to just run a test. So this was really how the core Zaiput technology works. Now I want to show you applications, which I hope you will find interesting, taken from flow chemistry, which is where Zaiput originally exclusively used to work, and then to the more, let's say, recent developments of the Zaiput technologies, which means the use of Zaiput separators, Zaiput continuous separators, but for batch processes. And then finally, the use of Zaiput in multi-stage complex extraction, which can be applied to both batch and flow chemistry. So let's start with flow chemistry, which again, Zaiput, the name of our company, Zaiput Flow Technology. We are really the standard for phase separation in flow chemistry. And still today, really, it's when you are looking for a continuous separation in flow, you're thinking of Zaiput. So why does Zaiput exist? Zaiput exists because before Zaiput or without Zaiput, if you do a process in flow, there are many good flow reactors, but there aren't really techniques made for flow chemistry, other than Zaiput, of course, for a continuous workup. So what happened before Zaiput was that there were reactions done in flow, but then workups done in batch. That was pretty much the standard. Zaiput allowed our customers to really do a continuous setup where the reaction is in flow and the workup is in flow. Really developing a continuous flow chemistry process. And I want to give you a couple of examples on how the Zaiput separator has been used in the past. The first one is the synthesis of fluoxetine, which is a 3-step synthesis, starts with a diol reduction, move to an amination, and then finally an aromatic substitution. Workups here are needed between step 1 and step 2 to remove the aluminum salts, which would be incompatible with reaction 2, and then between step 2 and 3 to remove the water, which would hinder the reaction number 3. So what has been done in this published paper is to do a first extraction for the first workup with a 2-step extraction, but done continuously. And here you can appreciate the difference of doing a 2-step extraction in batch, where you would need to finish the first step for the whole batch and then move to the second step, or doing it continuously, where basically you can use 2 Zaiput separators in continuous and spend the same amount of time it would take just for one extraction. The second workup is quite interesting because reaction number 2 and reaction number 3 are done at 140 degrees C, and the whole sequence is operated at 17 bar or 1.7 megapascal. So you can see how the separator can really resist fairly high pressures and high temperatures, which basically means that you don't have to step down the pressure or the temperature before you go into a Zaiput separator. The second example is one that I particularly like. It comes from a work of Professor Kappe of the University of Graz, which is very active in the field of forbidden chemistry, basically all of those chemistries that are quite hazardous to do in batch, whether because the molecule is unstable or whether because it's just not very safe to do them in batch. And he uses often our Zaiput separator for this type of processes. In this case, you can see the on-site production and use of cyanogen bromide, which is synthesized in flow and then immediately separated and sent in DCM to the next reaction. So it really, it's really a matter of a fraction of a second or a few seconds, the time it goes from when the cyanogen bromide is synthesized and then when it's used for the second reaction. So you don't need basically to have a buffer vessel for a gravity-based separation, which with other technology you would need. The last example taken from flow chemistry is also work from the University of Graz. It shows the synthesis of mesazoline. And I also particularly like this one, which is why I chose it today, because it shows how the Zaiput separator is used in two different locations. The initial one is basically an acid-basic wash of this stream where the Zaiput is used twice. And then at the end of this path, the Zaiput is used as a gas-liquid separator, which is something we haven't seen yet, downstream of an hydrogenation. So you see the hydrogenation here, you see the back pressure regulator to keep the line under pressure, and then finally there is a Zaiput to effectively remove bubbles of gas from the liquid stream. On this point, I want to show you the last let's say, use of the technology in flow, which is, again, the removal of gas bubbles from a liquid stream, or, of course, the removal of droplets of liquids from a gas stream. So typically, the way that the device has been used in this case, and just to clarify, we're talking about exactly the same device with exactly the same membranes can be used for a gas-liquid separation. You can see here how the device is basically used to take out bubbles of gas, or in some cases, it has been used to remove a volatile component from a liquid stream by injecting gas and then, of course, separating it with the Zaiput device. Now, we have seen how the device is used in flow chemistry processes. As I was telling you, I would say coming from feedback from customers, we understood that our technology actually, especially at large scales, had a very important, it was an important source of advantages for batch processes. So what are the issues that our device can solve when it comes to batch processes? And so basically turning them into hybrid ones. The first one is that, and let me throw some random numbers. You have a reactor with, let's say, 1,000 liter capacity, but you run the reaction only in 500 liters of those 1,000 liters because you have to leave some empty space for the extractive solvent to be poured in. And then, of course, you will have to mix and separate. The second issue is that if you have processes, we have already touched on this, but if you have processes where you have multiple extractions, 2 or more, of course, you will finish the extraction number 1, spend, let's say, 2 hours, and then move to extraction number 2, spend 2 more hours, and then to extraction number 3, 4, 5, and 6. So really making the time it takes to complete the workup much longer. Issue number 3 is, of course, very trivial. It's all of those situations where just the separation by gravity doesn't work well. You know, it takes a long time. It creates emulsions. It's not very repeatable. You need an operator to monitor where the interface is. One way or another, you are not getting good separation just based on a gravity approach. So how can we solve, especially the first issue, which is the reactor used at half capacity? We can supply our ZFox platform, which of course is based on our separator, exactly what you have seen before. But together with the separator, it comes with 2 pumps and one section of inline extraction. What does this allow you? It allows you to use the full capacity, this full 1000 liter, to go back to the numbers I was using before, the full 1000 liters for the reaction. And then you can just take the solvent from the IBC or the solvent container, connect the 2 feeds to the pumps, use our pumps. You can regulate and control your pumps to determine the phase ratio and the speed. You will basically mix the 2 phases and then flow through the static mixers to complete the extraction. So this is an inline, a section of inline extraction that we achieve through static mixers. And we developed a modular system where basically you can make this section longer or shorter, depending on your process, so that for, let's say, easy processes to extract, we can keep that line short. For harder processes, we can keep that line longer to allow the mass transfer to happen. Long story short is that by the time the biophysics stream completed the path through the mixing units, the system will be at equilibrium, ready to be separated and extracted. So again, what are the advantages of all of this? As I said, using the full capacity. And before I continue, I want to show you again another little video on what these mixing units do. So I will let this video play in a second. You can see that the bottom part of this tube, this is a zoom of that inline extraction section. So the bottom part is where the mixing elements are, which are static mixers, if you are familiar with them. And then the second part of the tube is just empty tubing for the droplets once they are mixed to get in touch with each other and for the mass transfer to take place. So I will play this video so you can see how it looks like. So you can see how it gets mixed, and then when they come out of the static mixer, the 2 phases now have the time to interact with each other. So again, we can make this section longer or shorter, but we want to make sure that, of course, and we will make sure that your phases will reach equilibrium by the time they enter the Zaiput separator. So let's look at the time impact that this platform can have on your processes. So, of course, if you do a reaction in batch and then an extraction in batch, what you will do is pouring the second phase in the reactor after the reaction. Then you will have to mix the 2 phases together, but not too fast, of course, otherwise you will emulsify them. You can wait that the 2 phases will settle by gravity, and then you will have to, of course, drain one of the 2 phases. Now, taking from processes of our customers, looking at some literature, we have seen that on average, each one of these steps take 30 minutes. Typically, the separation takes actually longer than 30 minutes, but just to make round numbers, let's say that you're spending 2 hours for a 1000 liter reactor to complete the workup step. So what the ZFox platform does is basically allowing you to move all of these batch steps into continuous ones. So adding the second phase becomes a continuous concept. Mixing the 2 phases becomes a continuous process. We do that through our static mixers. Separating and draining, of course, happens through our devices. And so if you think about our 2400, let's round it to 2000 liters per hour separator, it means that we can reduce this time from 2 hours down to less than 1 hour, processing twice as much product because now we are using the full capacity of the reactor. And of course, if you're thinking now of processes where you have to wait maybe days for the separation to take place, I think that those are the situations where really it is worth to give it a shot with a Zaiput separator and see how the separation would really accelerate. And so you're saving time. And as you know, time is, of course, money at the end of the day. To show you a picture of the device, this is the ZFox platform at the 3000 scale. So there is one step further, which is the 40,000. Again, 40 liters per minute. But this shows you really well how the platform is built. You can see the two inlets for the pumps down here. One is going to be for the aqueous, the other one is going to be for the organic. After this, the two streams will mix together. They will go into a section of inline extraction. So this is exactly where the static mixers are located. And then once they are fully extracted, once they reached equilibrium, they will go into the separator, and then you will basically collect the two phases from these two outlets, extracted and separated. You cannot see the screen, but here is an HMI where basically you monitor a few sensors that are installed in the platform. And most importantly, you basically set the flow rate of the pumps. And of course, you start the platform. To anticipate some of the questions that are received at this point, the platform is ATEX compliant if you need it to be ATEX compliant, and it is GMP compliant as well if you work in a GMP environment. Now, as I was saying before, again, we have seen this a little bit already, but if in your batch processes, you're now doing extractions in batch, and basically you're spending a multiple of the time it would take for just one single extraction, we can make, of course, the ZFox platform with two or more separators so that your feed will just, at the same time, will receive multiple extractions. Now, in this diagram, you see that the phases go to the same solvent vessel, but of course, this can be different solvents. It depends really on what you need for your process. Now, I mentioned before that on the SEP 40K, so the 40 liters a minute, the fourth and biggest separator, there is a slightly different way that we approach separation. It's not that different. It's just a little bit of an upgrade on the technology, which was needed at these large flow rates. What we do is basically, if you remember what I explained before, one phase with our technology is a permeate phase, and the other phase is a retentate phase. What we do with this larger separator is actually now having two permeating phase. So one, the organic phase, of course, will go through the hydrophobic membrane, and then the aqueous phase will go through the hydrophilic membrane. What this allows us is basically to avoid the situation of retention. Retention is when the hydrophobic membrane is not able to attract, if you let me use this term, to attract all of the organic phase, and some droplets of organic phase will basically escape the device from the aqueous outlet. With this system, of course, that issue will be reduced massively, because now, even if a droplet, let's imagine a droplet which doesn't get attracted initially by the hydrophobic membrane, will basically not be able to permeate the hydrophilic membrane, so it will basically bounce back and finally be separated by the hydrophobic membrane. So that's why we typically can increase the flow rate even more going through this separator and really getting up in a more than linear fashion. Now, this is a picture of the device. It's of course bigger than the other devices, but I would still consider it a compact unit. You can see here the dimension. It comes on wheels, so it can be moved if you're planning to use it on several different reactors. It has a modular throughput, meaning that on this larger device, you can really choose the membrane area. You can make the membrane larger by adding more membranes in the device, so that you can basically increase or decrease the capacity of the separator as you wish. The membranes are basically installed in cartridges, so they're very easy to replace. The device is made for an industrial type use. And the two phases, as I said before, where there will be permeating and permeating. So you will not have any more a permeating and a retained phase. And I'm happy to take questions on this larger device at the end of the presentation. Now, the third and last section of this presentation is related to complex multi-stage and particularly countercurrent extractions. So when do you use multi-stage countercurrent extraction? You use them, and actually what really is multi-stage countercurrent extraction? Let's start from the concept of the partition coefficient. Partition coefficient is a value that indicates how effectively one solvent is able to extract a certain compound from one phase to the solvent. So it means that with a partition coefficient equal to 1, with a 1-to-1 mixture of water and the organic compound, the organic solvent is able to extract only 50% of our compound of interest. This is just an hypothetical case. If we consider a partition coefficient equal to 5, for example, at this point, we will be able to extract 83%, so we will be able to extract more. So when do we need multi-stage extraction? We need it typically in these two scenarios. The first one is that our extraction is just not very, it doesn't perform much, meaning that, for example, if you have a partition coefficient equal to 1, you're only extracting 50% of your compound of interest. So you either use multi-stage steps or you increase the volume of your solvent, but of course that has financial and environmental impacts, and you reduce the concentration of your compounds in your solvent. Scenario number 2 is where you have molecules that tend to behave very similarly with a very slight difference. Think about a situation where you do an extraction from a botanical oil, where you have multiple compounds, sometimes very similar one another, and you cannot selectively really extract only one with one single extraction. You really want to magnify this partition coefficient information. In all of these cases, you can use multi-stage extraction. So what multi-stage extraction does, and again, particularly in countercurrent, is to keep exactly the same volumes of the two feeds, so of the organic and the aqueous. So let's consider still a 1-to-1 ratio as before, but rather than doing just one mixing and then one separation, you will have one phase going from separator 1 to separator 5, and then the other phase going from separator or stage. I use the term separator and stage as synonyms now, but basically the aqueous phase going from stage 5 all the way backwards to stage 1. And so if we take a central stage, let's call it stage N, just for the time being, what happens is that we will take the organic from stage N-1, mix it with the aqueous from stage N+1, go into a section of inline mixing, and here we use the same technique as before, so inline extraction through static mixers, to finally go into stage N, which is the separator, which will send the aqueous to stage N-1, and the organic, the purple arrow, to stage N+1. All of this, again, allow you to increase the extraction efficiency of your process without increasing the volume of solvent that you use. So let's take the example I was mentioning before, a solvent ratio of 1-to-1 and a partition coefficient equal to 1. In a situation like this, it means, as you've seen before, that with one single stage, basically one simple extraction, you are extracting only 50% of your compound of interest. What you can do is increase the extraction efficiency of this process by just increasing the stages, and once again, by keeping the same volume of the extractive solvent. So by just making that chain longer, at each step you extract a little bit more. So think about your processes. If there is a process where you want to increase the extraction efficiency, keeping the same volume of solvent, we can help you. If there is a process where you want to keep the same extraction efficiency but reduce the volume of solvent, we can help you. So in general, we can help you with improving the extraction efficiency. Now, all of this related to countercurrent extraction, it's not something that Zaiput invented. It's something that has already been there. What Zaiput invented is a better way of doing countercurrent extractions, especially when you look at laboratory scale. So this is our platform for countercurrent extraction. It comes with 5 separators when we're talking about 10 milliliters per minute scale. Why is this platform so successful, and why did I say that it does countercurrent extractions better? First of all, it has an extremely low volume. So you're looking at less than 3 milliliter per stage of internal volume on this platform, which is not something comparable with other technologies. So it means, and it reaches steady state in about 4 to 6 residence times. So it means that if you have expensive, very valuable solutions where you are running an optimization to find the ideal conditions for a multi-stage extraction, You don't want to waste 1 liter for each data point. You want to waste or use a few milliliters, and this is what our technology allows you to do. The other aspect is that we can, with each separator, you always match one theoretical stage of extraction, which is not something you can do with other technologies. Why is this the case? Because on each coil, you can get a complete extraction. Again, we bring the phases to equilibrium, and then with each separator, you separate perfectly the 2 phases. And so it means that if you're using, let's say 4 or let's say 5 separators, you are matching the 5 theoretical stages of extraction. This means that if you're using the platform to scale up processes, you will exactly replicate it. The scale up becomes a very trivial and very simple process. So you will just have to match the number of separators you use on the larger scales, and then increase, of course, proportionally the flow rate. The only difference between these 2 platforms, the platform at the 10 milliliter scale and then at the 200 scale, and of course the technology is available at the larger scale. The only difference is that at laboratory scale, we achieve a continuous extraction without using any static mixer. So we have found that it's enough to basically flow in a long enough tubing with a small diameter, the biphasic stream, to create enough contact area and enough convective movements to achieve a complete extraction, while on the larger scales, we need some help from static mixers. And in this video, you can see what it means. So when we work at laboratory scale, we just basically flow a biphasic stream, as you can see, through the coil, and then it will go into the separator being extracted and separated, fully extracted, and then the separator, of course, will separate. And this is the video you have seen before. When we work at larger scales, we use the help of static mixers to really create a droplet breakup and achieve a complete extraction. Just a quick example. I know the time is running out, so I will try to wrap up very fast. This is an example where the technology has been used at the 10 milliliter scale and the 200 milliliters per minute scale, and demonstrated how the technology is very easily scalable. And all of these papers are available. If you want, I can send them to you. In this case, the technology was used actually initially as a single separator after a reaction done in a carbonic flow reactor to separate the biphasic reaction stream. And then the multi-stage technology was used to recover the phase transfer catalyst and send it to the aqueous extract on a 3-step multi-stage setup. This is particularly interesting, this process, because this is a mixture that doesn't separate well by gravity. It achieves an okay separation in 80 minutes, but it takes 19 hours to really get a perfect separation. So imagine doing this multi-step process where each single step you will have to spend 19 hours. Finally, some of the reasons why people choose us when it comes to countercurrent extraction versus other technologies. Now, I know what you may think now. I may be biased, of course, because I represent Zaiput, but these are quite objective reasons why people choose Zaiput versus other technologies. And I would like to highlight really the main ones. The first one is that working with Zaiput, the scale-up process will be extremely simple. Second and third reason are that handling emulsions or liquids with similar density, only Zaiput basically allow you to do so, especially the density is exactly the same. And then probably what, in my opinion, is the most important reason is that the internal volume of the platform when Zaiput, with the Zaiput technology is orders of magnitude smaller than competing technologies. And so really, if you use valuable, expensive material for your optimization, working with Zaiput would allow you to achieve data points in a fraction of the time. Now, so we've seen a little bit of who Zaiput is in our history. We have seen what the core technology does, phase separator, liquid-liquid and gas-liquid separator. We have seen uses of the technology in flow chemistry. We have seen how the technology nowadays with our larger separators is used in batch processes. And finally, in this last section, we have seen how the technology can be used, and it is used in countercurrent extractions when one single stage of extraction is not enough. So with this, I have completed my presentation, and I thank you very much for your attention. I hope it was interesting, and I'm happy to take any questions if you have any.
Hi, Lorenzo, thank you so much. Yes, please keep the control because maybe you can use your slides for questions. Are there any questions so far? Okay, we have one question that say, thank you for your presentation. I'm used to work in batch with suspensions 5 times the max reliability. How would you transfer a process in batch to use separation in flow? Dilution 5 times. What happens if particles participate in the tubings? You showed an example removing all salts.
Yes, so of course, this is a very good question. If you can keep all the solids in solution, basically by diluting, for example, that helps us tremendously. Of course, the separator works better if there are no solids. If that's not possible, of course, adding 5 times the volume sounds a little bit too much. So if you can dilute a little bit, that would be ideal. But if you cannot keep all the suspension in solution, you can, of course, filter. So in this case, you can see how there is a filter installed in the platform. So we always provide filters because taking out the solids help us. If for any reason you cannot filter or you cannot filter entirely, what will happen is that over time, the membrane will clog, which is not necessarily a big deal. It depends on how fast the membrane will clog. If you have a slurry, of course, we are not the right technology. But if you have just a normal content of solid, maybe the membrane gets clogged in more time that you need to complete the whole batch. So it's, of course, impossible to provide a one-fits-all answer. What I can tell you is that the scalability of our devices will allow you to have an answer of what is the impact of the solids on your process by running some tests at laboratory scale. You see how the solids impact the process, and then you will have exactly an idea of how the process would work at industrial scale. But of course, if you can remove the solids, whether keeping them in solution or filtering them out, that helps tremendously.
Thank you, Lorenzo. Just would like to remember to everybody that there is also opportunity to send a message directly to Lorenzo via email. Okay, so I have a couple of questions for you, Lorenzo. I'm very interested if the membrane is chemically stable, and how often should it be replaced in industrial scale operation?
Yes, so the membrane is actually in PTFE, basically Teflon. So it's really extremely stable. We come from flow chemistry, which is a space where often very hazardous, very corrosive chemistries are done. So the membrane is very stable. You will not have any issue with that, really. And actually, I would encourage you to consider processes that where material of compatibility with other technologies is not so good. Regarding how often it has to be replaced, we go back to the previous question, meaning that if the membrane keeps separating and it doesn't get clogged with solids, if your system is solids free, you can use that membrane, and typically you can use it for a very long time. The question is, does the membrane get clogged with solids? If so, you just have to properly replace the membrane in between, for example, each batch or each few batch. And so there isn't also in this case a one-fits-all membrane. The question is, what are the solids that are present in your stream?
Okay, thank you. So I understood that the membrane in the device can act also as a molecular filter for dissolved solids, no, or other molecules?
Actually, no. This is a very good question because the pores of the membranes are very large, and so we don't filter the molecule based on size. So we let basically all of the, let's say, the organic phase go through with all the molecules that are dissolved in the organic phase. So this is a good question. Just to clarify what the device does, the pores are so large that basically we just do a phase cut, and everything that is present in the organic will stay in the organic after separation. Everything is present in the aqueous will stay in the aqueous. But that's a very good question.
Thank you. Thank you. Thank you, Lorenzo. If there are more questions, you can use also the chat or send an email directly to Lorenzo. Waiting just a few seconds if there is any question that arise in the meantime.
I would say if there's any question, of course, I welcome questions also in the next few days or months. Please use my email address because the chat, I think I would not monitor it any longer. So, but please, for any curiosity, any question, please do reach out.
Yeah, in the meantime, I have just last question for you, Lorenzo. If for example, I add a mutually miscible solvent, for example, acetone in a biphasic system, can I still separate the two phases with the Zaiput separator?
You can, you absolutely can. So let's take the example of a water and ethyl acetate system, and you add acetone, as you said, to it. The acetone will basically bring the two phases closer to each other, but as long as the system is biphasic, you can still separate. And then, of course, a fraction of the acetone will be in the water, a fraction will be in the ethyl acetate, but as long as the system is biphasic, you can still separate. Of course, if you add enough acetone, the system will become single phase, so everything will mix. And in that case, we cannot separate any longer. But if there is, which is very common to have a third solvent, let's say, and if the system remains biphasic, we can absolutely separate.
Okay, just see if there are more questions, and otherwise, Lorenzo, I can just say thank you so much for your clear presentation about your system. Is very interesting, and I hope the people that attended our webinar will contact you to get more information. So thank you so much. I just want to take this opportunity to remember the next event of a PCTG group, the 8th of November, about the one-day symposium about the digital future of process chemistry and technology. It should be online. They will be online or at the Burlington House, London, at the Royal Society in London. So Lorenzo, thank you so much, and take care, and all the best to everybody, to you and to all the people that attended our webinar.
Thank you, Giuseppe, and again, thank you for inviting me. It was a pleasure, and thank you everybody for your attention.
Thank you. Bye. Bye-bye.